So let's go through the theory behind the definition of the derivative one last time real quick. And all of this pretty much is written on the handout, so you don't have to, you just kind of need to follow through me, but we did this Friday. So back in geometry, when we studied tangent lines, we did it with circles. And a tangent line would be like this one right here, and it intersected the circle at one point. Remember how it would make a right angle, and there would be all kinds of properties. And then what kind of line would this be? A secant line. It intersected it twice. So in geometry, that was the tangent, and this was the secant line. But when you have a general curve, it's a little bit more difficult. For instance, you can't really use the intersects at one point rule because, like right here, this is a tangent line. But notice it's going to intersect the curve down here. So you can't really use that geometry definition about intersecting the curve at one point. So we have to have a slightly different definition of what the tangent really is. So what happens, if you read this carefully, it says, finding the equation of the tangent line simply boils down to finding the slope of the tangent line. And it says, since we already have the point of tangency, if we knew the slope, we could write the equation right now. We can approximate the slope of the tangent by using a secant line. A secant line is a line through the point of tangency and a second point on the graph as shown below. So what you'll see down here is this is x equals c. That is the point of tangency. I want to know what the tangent line is right there. So I pick a second point on the graph. Well, the way that point was chosen is how far over did they go? How far over did they go? Delta x. What does delta x mean? Change in x. That's that little distance there, isn't it? And so if I go over delta x, I'm now at c plus delta x. Hence, that's where this point came from. It is c plus delta x, f of c plus delta x. Well, the tangent line is not drawn on that picture yet. That's what we want to. That's what we're going to define. This is how we're going to define it. So this is the way you define what a tangent line is. So you start out with a secant line, and we're going to use it to approximate the slope of the tangent. All right, so if you continue here, it says this point right here, that's the one we're concerned with. So we pick this point Q right here, and we're going to find the slope of that secant line. So we did this Friday. If I want to do the slope, which is change in y over change in x, or back in Algebra 1, you learned this formula here. What would be my slope using those 2 points here and here? F of c plus delta x minus f of c over c plus delta x minus c. And then what happens is what? C's cancel, and we get this thing. What's that called? Difference quotient. You need to know that name. It is the difference quotient. All right, everybody with me here? So we use something that we can easily define, which is a secant line. And we can use algebra and get the slope of that secant line. Now, how are we going to turn that thing into a tangent line? What can I do to those 2 points to make the secant turn into the tangent line? Make what smaller? What up there in that picture, what value do I want to make smaller? Delta x. The distance, right? I want this distance not to be that big. I'd like it to maybe be there, right? Close to 0 as possible. So that's not good enough right there. I want it itty little bitty right there. It's going to be so small the human eye can't detect it. I want to get it as close to 0 as possible. So I don't want Q to get small. I don't want C to get small. I want delta x to get as close to 0 as possible. That's going to make the tangent line come out of the secant line. The secant line, those two, point P and point Q, are going to be so close together that they're basically going to make what we're going to call the tangent line. So how do we do that? Okay, well, that's this next thing. The beauty of this procedure is that you obtain more and more accurate approximations to the slope by choosing points closer and closer to the point of tangency. Now circle this right here. This is important. As delta x gets close to 0, the slope of the secant approaches the slope of the tangent. So here's what ends up happening. If I draw a line through those 2 points, and then let's say I draw a line through those 2, and then let's say I draw it through those 2. Okay, what will end up happening is that the secant line gets closer and closer and closer to it basically becomes the tangent line. So what our definition does is we start out with this definition of the tangent line having slope m. And we say, if you look at this, I do the limit of the slope of the secant. That's what this is right here. And that's what this is right here. That is the slope of the secant line. And basically what happens is, if you make delta x as close to 0 as you possibly humanly can, what you get is the slope of the tangent line. Okay. Make sense? All right. And you'll notice we have these 2 little stars here to cover the possibility of a vertical tangent line. Let's say that you did that limit and it was continuous at C, but you got infinity for an answer. Well, what happens in that case is you'd have a vertical tangent line. Okay? And then they ask the questions, what type of graphs have vertical tangent lines? Alright, well, you should know of a couple. One of them, this is the most famous one, is cube root of x. Cube root of x right here. If you were to look at the tangent lines, what happens is it has a vertical tangent right there. If you think about it, it kind of makes sense, because look at what happens as you look at the tangents as I get closer and closer to right there. You can kind of tell they go more and more vertical as you get close to the origin, and then when it gets past the origin, then they go away from vertical. So that's kind of the most famous one, but we're going to see others besides that. Okay, so that's the theory behind the first definition of the derivative. Okay? All right. So, what happens then is we go from that to saying, well, we're going to use the slope of the tangent to define the derivative. So, on that formula there, we had f prime of c was equal to limit delta x approaches 0. Remember how it had f of c plus delta x minus f of c over delta x. We had that formula right there. I mean, you just wrote it. You don't have to write it again. That only tells you the derivative at one single point c. Well, what if I wanted to know a formula that would tell me the slope of the tangent everywhere? Well, what they simply did is change the c's to x's, and they give us this definition of the derivative that you're going to want to memorize. Okay. Remember, though, that in working problems, which we will do tomorrow, that sometimes it's easier, even though delta x makes the theory make more sense, sometimes we'll use h instead of delta x to make the algebra a lot easier. And you remember, that's what we did in pre-calc. When we did difference quotient problems, we would always do the f of x plus h minus f of x over h, because that's easier to work with. But when you're doing the deriving, when you do the theory, I want to see delta x's so you know what in the world you're talking about. In practicality, we'll say that delta x is equal to h just to make it easier. So what are the symbols for the derivative? Okay, well, you might remember some of this from last year. One of them is f prime of x. That's one of the biggest ones that we'll use. dy dx is another one. Where do you think that comes from, dy dx? The slope. What about the slope? Exactly. And all they did is, instead of using deltas, what they use? D's, which is just standing for delta, right? Those are the most common ones we'll use, and this one, like y prime. So, I mean, there's others, but those are the three most common ones that we'll use. All right. So that's a rehash of the theory that we did on Friday. Make sure you can write this out, deriving. which I'll probably give you, like, do you see how this picture was here? I'll give you that, but I won't have anything labeled. Alright. Now, go over to where you can find, we're going to skip over a page in your notes, and find where it says differentiability and continuity, and see where it's got the alternate definition. Alright. Now here is the theory behind this. An alternate way of doing the definition of the derivative is we're going to call this point CF of C again. But this time, the second point used to create the secant line, we're going to call it XF of X. So what happens, and you need to correct this right here, this is not C right here, this is X. Correct that on your handout. So if I do the slope of the secant using change in Y over change in X, what would you get? Using these 2 points, what would you get? F of X minus F of C over X minus C. Now, X minus C is this distance right here. That delta X there, the distance is X minus C. Well, do you remember how on the regular definition of the derivative, we wanted delta X to go to 0, didn't we? Well, on this problem, X minus C is your delta X. But we want X to approach C. Yeah, you move C to the other side of that. That arrow is kind of like an equals. So you want X approaches C. So the theory is that if I make this distance right here smaller and smaller and smaller and itty bitty, this point's going to get closer and closer and closer and closer to the first point. And what will that secant line turn to? Delta X will go to 0, but it'll turn to a tangent line, right? So the slope of the tangent, which we're defining to be f prime of C, is the limit as x approaches C of this. So that's the theory. Okay. So now we're ready to actually do some problems now. So on your homework, 61 through 69 odd, they're going to ask you to do some problems with this alternate definition of the derivative. And remember, the limit exists if the limit from the right's the same limit from the left. Since these derivatives are defined by limits, our limit rules still apply. We have a limit from the left, limit from the right. So here's the first thing I want to look at. Okay, and this could be an example on the homework. They might say f of x is absolute value of x minus 3. Find f prime of 3 if possible. Okay? Alright. So what we're going to do first, we're going to do it algebraically, and we're going to do it graphically so you can get an idea of how this alternate definition works. Alright? So let's do it algebraically first, and then we'll look at the graph to see where it's coming from. So if I was going to do this algebraically, I would say, okay, f prime of c is the limit as x approaches c of f of x minus f of c over x minus c. Isn't that the definition? Sure, right? Where do I want to do the derivative at? 3. So 3 goes where? C. So everywhere there's a C, I'm going to put a 3. With me there? All right. Well, what's f of x? It's absolute value of x minus 3, isn't it? So my function was absolute value of x minus 3. How do I find the value of f of 3? How do I find the value of f of 3? Plug it in. Where? F of x, right? Duh, right? Plug it into f of x. Get 0. So if I calculate this limit, I'll get the derivative at 3. Okay. All right. Now we already know the answer to this limit, don't we? It does not exist, right? We already know it does not exist. Now, let's make sure we understand why, because we're going to do this right here. And then we got to keep these things straight. So we'll get to those answers, those questions in just a minute. So we said the derivative does not exist. What does that mean? Okay, so that means f prime of 3 is undefined. What does that mean? That means f is not differentiable at x equals 3. Okay. Now that's the algebra, right? Now let's figure out from the graph why this algebra ended up being that way. So let's just plot some points here if you don't know what absolute value of x minus 3 looks like. I would hope you would know because it's translated how? 3 units to the right. All right, so if you don't know, let's plot some points. So if we plug these numbers in, we're going to get 3, 2, 1, 0, 1, and 2. All right, so first, let's make sure we understand the difference between continuity and limits, and differentiability. We've got to get that straight right here. So first of all, what is the limit as x approaches 3 of absolute value of x minus 3? Now forget derivatives, just the limit. What is the limit of that? 0. We could just plug 3 in and get 0, right? How could I get that from the graph? Limit from the left and the right, it's both going to that point right there, it's 0, right? Would you agree that f of 3 is 0? Because this is the x, this is the y, right? Is it continuous there? Yes. So the answer to this is yes, it is continuous because the limit at 3 of the function is equal to f of 3. So definitely is continuous. But now let's talk about differentiable because we already said it wasn't. Let's look at graphically why the derivative doesn't exist. Now you're going to hear me guys say this over and over and over and over again. The derivative tells you the slope of the tangent. The slope of the tangent tells you the derivative. What is the slope of that part of the graph? That slope is 0? 1, right? So, what is the slope of this part of the graph? -1. Alright. Now, I want you to understand why that matches up with this right here. You're going to see in a second why this matches up. Okay, jot this down for me. Alright. So we did here the limit as x approaches 3 of that absolute value stuff. Think back to when I asked these questions here. Limit from the right, limit from the left. Okay, how would we find those answers? Plug numbers in, right? Remember how we would do like 3.1, and then we'd plug in what? 2.9. Yep. Looky here at the answers. Aha. See what this is equal to right here? Those numbers were the slopes up there, weren't they? Alternate definition of the derivative tells us that. Those are the slopes. This is f prime of 3 from the left, and this one is f prime of 3 from the right. They are different, aren't they? Hence, not differentiable. No derivative. Not differentiable just means there's not a derivative there. And then we can see by just looking at the graph that those derivatives are different, right? That slope's 1, that slope's -1, they're not the same. Okay. So the question here then, to answer these things, what is the derivative as x approaches 3 from the left? Well, we just said that was what, -1, and this was 1, so it's not differentiable. All right. Then that gets us, and if you'll do this at the bottom of the page, this gets us to where we then start looking at, okay, well, physically, if I see a graph, how can I just look at the graph and kind of tell where it's not differentiable? So f is not going to be differentiable in these cases. Just find somewhere, you don't need a lot of room. So here are what you look for if it's not differentiable. So the first one is, it's when it's not continuous. If it's not continuous, automatically not differentiable. The second one is what we just saw on absolute value. What's happening right there at that point? Yeah, but it's a radical change in direction, right? How would you describe that? What kind of point would you say that is? Physically. Is it smooth? What kind of point? Okay. Well, we call it a sharp point. Okay, so this is like absolute value. If it has a cusp looks like that. Now, the one that looks like this is x to the 2/3 power. I think that's the one. Which actually, I think I've got it backwards. I think that kind of looks like this. But there's a cusp here and here. So you look for, where is it not continuous? You look for sharp points. Well, you look for cusp. And then the fourth and final thing you look for are vertical tangents. And I already showed you cube root of x, which has that. So this part should be the easiest part of the homework then. You'll have a couple of those with the alternate definition. We'll do some more of those tomorrow. But what's going to happen is they're going to give you a graph, and they're going to say, okay, where is it not differentiable? So here's two graphs right here. This is the easy part. So it says, I don't know if you can see this here or not, but there's the graph right there. So where is it not differentiable on that number 5? Where is that at? Okay, so there's two ways to word this. We could say f is not differentiable at x equals -1. But the book wants to know, where is it differentiable? So how do you write everywhere else? Right. Excellent. Okay. And then what about this graph here, this number 6? Where is it not differentiable at? Negative 3 again, yeah. And then y. Okay, this one was because it had the cusp. What's wrong with number 6? Vertical asymptotes. In other words, it's not continuous, right? If it's not continuous, it's not differentiable. So see, I've got this, clearly, the vertical asymptote, it's not continuous there. So it is differentiable, though, everywhere else. So it's differentiable from negative infinity to negative 3, negative 3 to infinity. Now, this is what's hard on this one right here. It is continuous there. It's continuous because the limit from the left and the limit from the right are the same, and then there's a point there. The reason it's not continuous, the reason it's not differentiable, is because it's a cusp. And what the cusp is doing, look at these tangent lines. What are they becoming more and more like? Vertical, which has what kind of slope? Positive, infinity, or undefined, right? See, vertical tangents don't have a slope.